Well, this is an interesting example I want to do, and that is an aviation example. So let's imagine we have an aircraft. So we have an aircraft here, wings, tail, and so forth, and it's in level flight. So we have an aircraft, and it's in level flight. So what are the forces acting on it? Well, we got the thrust due to the engines. Okay, we've got the drag force, that's the air resistance. We've got the weight, and then we got the lift, the aerodynamic lift. Now, if it's in level flight, then the aerodynamic lift has to equal the weight. Now, the aircraft is going to bank. So if the aircraft is banking, let's say it's banking at 35 degrees. Now, what's going to happen? Aerodynamic forces are going to be in the same direction, the same magnitude, unless you do something with the aircraft control surfaces. All you do is adjust them, and then you move the control surfaces back into the straight position. Now, unlike a car, when you turn the wheels forward, it starts going in the direction the car's pointing. For an aircraft, it doesn't stop banking. You have to turn out of the banking. So you adjust it to put into a bank. When you put the ailerons back in the level position, it starts flying exactly like it is there. All the forces are back. You don't torque it back in the other direction. So you got to turn out of it. So that means that the pilot would have the controls looking like they're flying level, but the aircraft's tilted over like this. Well, as the aircraft is tilted over, then what's happening is there's a component here of that aerodynamic forces that's to the side. So the aircraft is flying along component to the side, and so that component to the side would cause it to move in a giant circle with some radius. So I want to know what's the radius of that curve right there, of the circle the aircraft is flying in. Well, this horizontal component is going to be L sine theta. And so that is going to be a centripetal force, mv squared over r. Well, L was equal to mg unless we do something else to the control surfaces. So that means r is going to be v squared over g sine theta. Okay. Now, if we assume that it's moving at constant velocity of 225 meters per second, okay, you need to know how fast it's going, but if it's going at a constant velocity of 225 meters per second, then 225 meters per second squared divided by 9.81 meter per second squared sine 35 degrees is 9,000 meters. So that means that r is 9 kilometers. So it's going in a circle, like a holding pattern of 9 kilometers. Well, it turns out it's not that simple. Okay, I said if all you do is adjust the aerodynamic surfaces so that you're banking, then that gives you a horizontal component. But let's look at the vertical component. The vertical component here of the lift is now going to be mg cosine theta. Well, there's still an mg downward. So that means that the total MA, so this is the total Y, force is minus mg plus mg cosine theta. The m's cancel, and so AY is going to be equal to g times cosine theta minus 1, AY 9.81 meter per second squared, cosine 35 degrees minus 1, AY is minus 1.77 meter per second squared. So that means that this aircraft here, okay, it's banked at 35 degrees from vertical, and it's accelerating downwards at 1.77 meter per second squared. Okay, now here's the really scary thing. The pilot inside because the forces acting on the aircraft are what are acting on the pilot, the force on the pilot is actually this way. You think about it. What do you got here? You've got an MA here. You've got a force making it go this way. You've got a force this way. So the net force is in that direction, the direction of the lift. So that means that inside, if you had a coffee cup, the level of the coffee cup would be level. It would look like you're flying level. You would feel like you're flying level even though you're accelerating towards the ground. For novice pilots, this is a problem. You fly into fog, or you fly into clouds or smoke at the end of the runway if there's like a grass fire or something, and what happens is a little bit of turbulence can push you into a slight bank. You adjust the controls to where you feel like you're flying level, and yet you're not. You're actually descending and accelerating descending. If you notice on the instrument you're decelerating downwards, you pull up on the stick, and so that increases the aerodynamic lift right here. And when you increase the aerodynamic lift enough, the vertical component balances the weight, and now you're no longer accelerating downwards. However, you still have a horizontal component that's in there, and so it feels like when that happens that you're tilted over. So what you do is, if you're a novice pilot, you adjust it until the tilt feels like it goes away. Well, when you adjust it to where the tilt feels like it goes away, you're back into the same situation of accelerating downwards. And so that means you get even closer to the ground. And so it turns out that you only have seconds to figure this out before you fly into the ground. And so that's why in aviation, this is called a death spiral. And the death spiral is something you can get into if you don't see the ground. And that would be, for example, if you're in fog or smoke that's near the ground, that's particularly dangerous. Or if you are in a cloud bank. It can also happen over a dark ground, whether it's in the desert or over water at night. And so if the ground doesn't have any lights on it, then you can't see that you're approaching the ground. The altimeter is going down, and you're trying to work out the problem. There is an artificial horizon that's on the cockpit dash. But a lot of novice pilots don't trust that instrument because it can sometimes not match the way you feel. And so if they fly by the way they feel, they inevitably fly into the ground. It's not just novice pilots. This can also happen to experienced pilots. I know of at least one case in which a commercial aircraft was taking off, and they were taking off, the pilot was taking off, and there was a grass fire near the end of the runway, and wasn't exactly near the end of the runway, but the wind had shifted, so the smoke was drifting right where they were flying. They flew through the smoke. A little bit of turbulence actually knocked the aircraft into a slight bank. One wing got more uplift than the other, and they started descending. And the pilot adjusted it to where it didn't feel like they were descending. And the other pilot, remember, commercial aircraft have two pilots in the cockpit. The other pilot wrested control from the first pilot and corrected, because otherwise they would have gone into a death spiral and hit the ground. So that actually does happen even with commercial pilots. So this is an example here of centripetal forces and aviation.